Welcome back, everybody. So today we are going to go over week 4, which is going to go over different types of chemical reactions. So first, let's talk about the theory of ionic theory of solutions. So there's a man named Arrhenius, and we'll talk about him a little bit later on, but he talked about how the ionic theory of solutions is going to account for the electrical conductivity of water. And so basically what he was saying is that when you have let's say that this is a container with water in it, and let's put some water present. And we take some kind of salt. Let's say it's something like NaCl. When this goes into water, this is what occurs. And so we'll get into polarity and the specifics of exactly what this means a little bit later. But NaCl, when it goes into water, is going to break into its ionic components because it is a completely soluble ionic solid. So Na plus Cl minus. And so in solution, you have Na, and it's surrounded by water molecules. Na plus is going to be surrounded by water molecules, and they're going to be making really weak bonds to the sodium, but they're going to be stronger than the bonds between sodium and chlorine. And so these little pods of sodium with some waters around it are able to freely float throughout the solution. And the same thing happens with the chlorine atoms. And so we get something similar with just the other side of the water making the bond. We have hydrogen making a bond there. And so these are also able to freely float. And so if you were to take an electrode and another electrode, a positive and negative electrode, then the negatively charged sodium, the negatively charged electrode would attract positively charged sodium. The positively charged electrode would attract negatively charged chlorine. And the transfer of these charges, the way that these are able to move around, is basically what is going to conduct electricity throughout the water. So water itself is actually not very conductive. But if you have salt in that water, something that is going to very easily move around its ions, then you can have some conductive fluids. And so this is called an electrolyte. So anything that dissolves into water is going to be able to give an electrically conducting solution. Anything that dissolves into water and gives an electrically conducting solution is an electrolyte. So if you have something that completely dissolves in water, then it's going to be an electrolyte. Most ionic solids are going to dissolve into water. Some are going to only do it slightly. Some are not going to do it at all, but most of them are. And the electrical current is going to be able to do exactly what I said. So the negative part is going to go toward the positive end, and the positive parts are going to go to the negative end. Meanwhile, this chunk of NaCl here is going to dissolve. It's going to break apart when you put it into water. So that's what defines an electrolyte, something that goes into water and conducts electricity. Non-electrolytes can dissolve in water, but they do not conduct electricity. So that's the difference. Non-electrolytes do not conduct electricity. Poorly conducting. Okay. So, solutions that are poor conductors have less or no ions. So that means that either you have pure electrolyte. Either you have pure water, or what you dissolved does not ionize. So, for example, sugar. You can dissolve sugar into water. It looks like this, C6H12O6, essentially. You dissolve that into water, and it does not break apart. So when we put water here, we're going to just get, if this is a solid, we're going to get C6H12O6 out. And this is just going to be an aqueous solution instead. With good conductivity, you have complete dissolution. So NaCl, doing the exact same reaction, you have H2O, and that gives Na plus Cl minus. And so this is going to be going from a solid to a aqueous ion and an aqueous ion. So now is when we're going to start paying attention to whether or not things have charges on them. And so as you can see from these images, before we go on, there is a battery hooked up to this and there's no current passing. Well, there's slight current passing. This light bulb is a little bit lit up, but with a good conductor, you have a full current passing through. And so a strong electrolyte and a weak electrolyte is what we're going to be talking about. So strong electrolytes are going to be things that completely ionize. So when we say almost entirely as ions, this is because all of the reactions that we will ever study are going to be reversible to some degree, which means that if you have NaCl going to Na plus Cl minus, this is also going to ever so slightly go back that direction where you are going to remake NaCl, but it's going to be such a small amount that it's basically unimportant, and so we can say that it is going to be entirely as ions, or at least mostly as ions. A weak electrolyte is going to dissolve in water, but it's going to only partially be. So something that's slightly soluble is, let's say that is going to be MgOH. Let's say barium. So barium OH is going to be something that sometimes, OH2, is going to be something that sometimes dissolves, but we'll draw the arrow like this because it's at equilibrium, which means that it's going to go back and forth between being a solid and being its ion. So Ba2 plus 2OH minus. So it's going to go back and forth between that, which means that it is a weak electrolyte, which means that it has a small percentage of ions. It could be like 75% BaOH and only 25% Ba2 plus and OH. Whereas this is going to be like 0.00001%, and this could be 99.9999%. So something like that, something along those lines. Okay, so these are just some words that we're going to be using. And so let's go through them. So we have a solute, which is something that is going to dissolve. Anything that dissolves into a solution is going to be a solute. So that covers both weak and strong electrolytes. And this is going to come into play later, so it's important that we know what a solute is. And then we have solvent. A solvent is something that is dissolving a solute. So usually we're going to be talking about water is usually the solvent. But there are tons, and I mean tons of different solvents, but the most common one is water, especially when we're talking about electrolytes. And so that is something that we should consider. If something is soluble, that means that it is a solute that is going to dissolve in solution. So it will make a homogeneous mixture, a solution, and when it's placed into a solvent. Insoluble is the opposite of that. It's something that is not going to make a solution. And so, for example, we're going to get into the exact type, what is going to constitute this, but AgI is not water soluble. Whereas something like NaCl, or you could, is water soluble. And so AgI is not water soluble. You could also say that it is insoluble. Same thing. It is also worth noting that the solubility applies to weak and strong electrolytes as well. So for example, you are water insoluble. Water insoluble. And this is true. I do know this because you have probably taken a shower or a bath or been in a body of water. The chances of that not happening are pretty high. So I do know that since you did not dissolve in that water and become part of that solution, you are not water soluble. You are water insoluble. However, sugar, C6H12O6, is water soluble. So just because it is not a strong electrolyte does not make it insoluble. It is a soluble species. Okay, so this is going to be probably the more, this is going to be more of a lot of information all at once, but we're going to go through each of the different things here. And so this is technically the rule system that the book would like you to use. And so I'll just give you a second to take a look at it and see what you can make of it. Okay, so let's go through each of these. So group 1A, that is the alkali metals. Those are water soluble every single time. You'll notice that this is the exceptions column. There are no exceptions. If your compound has a group 1A metal, or it has ammonium in it, then you have a soluble compound. So yeah, acetates and nitrates are also insoluble. So if you have an acetate, looks like this, CH3, C, double bond O, double bond, or single bond O, with a negative charge, that's going to be water soluble. You also have NO3 minus. These are going to be water soluble as well. So if it has a nitrate on it, it's going to be water soluble. Nitrate, that is important. Nitrite will not be soluble in the same way. If it has chlorine, bromine, or iodine, one of the heavier halogens, so halogens, except fluorine. Fluorine sometimes is soluble, so that is not the case. But most chlorides, bromides, and iodides are soluble. The exceptions are with Ag, Hg, which there are two different forms, so that's why it's on here twice, and lead. So that is silver, lead, and mercury. Those are going to be insoluble. But everything else is, if it has a chloride, a bromide, or an iodide, is going to be soluble. Sulfates, if it ends in sulfate, are going to be soluble except for group 2 metals, silver, mercury, and lead. So silver, mercury, and lead are going to show up a lot. If you have silver, mercury, and lead, then it's a good chance that you are not going to have something that is soluble. Insoluble cations. Ag, Hg, which can also be Hg2. So that's plus, 2 plus. This is also 2 plus. And what is it? Pb2 plus. These are going to be insoluble pretty much every time. Carbonates. Now we flip to things that are insoluble usually. So this first section here, rules 1 through 4, those are going to be soluble rules. 5, 6, 7, and 8, those are going to be insol rules. Carbonates, pretty much all carbonates are going to be insoluble. The only exceptions are going to be the group 1A and ammonium. So that means that all your alkali metals, if they have carbonate as well, then they're going to be soluble. Otherwise, it's going to be insoluble. Phosphate as well is going to be soluble or insoluble, except if you have the alkali metals or ammonium. And so let me just write this down. So soluble cations. That's going to be lithium plus sodium plus potassium plus. We're also going to put in the other ones because those are also soluble. Rubidium plus. It doesn't say it up there, but it's important that you know that all of those are soluble. And cesium plus. As well as NH4 plus. Those are going to be your soluble cations. So the first thing you want to do is look for your cation. Is your cation going to be soluble? Then probably the rest is going to be soluble. If it's going to be insoluble, then probably the rest is going to be insoluble. So we have phosphates that are insoluble. Again, we can go down to sulfur. So most sulfides are going to be insoluble as well. And hydroxide. Most hydroxides are going to be as well. There are certain ones that are going to be soluble. So we have calcium, strontium, and barium. Those are going to be soluble, depending on if they are bound to OH. So I just want to go back to this slide real quick. I did use barium as an example. Now, it is going to be soluble with OH, but it could be partially soluble. Really, you could replace this with anything. This is just an example to show what a weak electrolyte would be. Okay. And so when we look at the periodic table, let's look over here. So I'm going to make this a little bit bigger so that I can show more of what I'm trying to do. So these are going to be soluble. I'll change the color too so that it matches. All right. These are all soluble. These are mostly soluble. And that is with exceptions. And so these exceptions are going to be silver, mercury, and lead. And also, if you have a sulfide, that is also going to be insoluble. So S2 minus, as well as, but for solubility, we are also going to have NH4 plus. So when you are going to try to memorize the rules here, this is a good starting ground. Everything that is going to be a, everything that is a alkali metal is going to be soluble. Most of the halogens are going to be soluble as well. And so this would be a reactive nonmetal, but I'm not going to circle that because it doesn't actually just say halogens. If you have one of these, the silver, mercury, or lead, then we will not have something soluble. Okay. Okay, so let's go into these rules a little bit further, just to reiterate. If you have a group 1 metal, it will be soluble. So that is going to be all alkali metals right there. All alkali metals and ammonium are going to be soluble. The only exception is with S2. And actually, if we look back at the rules, that's not exactly true. So let's actually scratch that out. That is not true. The notable exception is not going to be true. The everything with these is going to be soluble. If you have something bound to a halide, where that is iodide, chloride, or bromide, that is going to be soluble for the most part, except when it's bound to lead, mercury, or silver. And so mercury can exist as Hg or Hg2 with a bond from mercury to mercury. Any of those are going to be soluble. If you have a polyatomic ion, it will likely be soluble. And we go back here, polyatomic ions, sulfates are all going to be soluble. Really, if you have a polyatomic ion, it's best to just check. It'll likely be insoluble. So that is going to be carbonates, phosphates, notable exceptions SO42, and I'm actually going to include NO3- there because nitrates are also those are also going to be soluble. And if you are unsure about it, I would just check it, just look it up, because otherwise it is not going to work out. You don't want to just guess, you want to be 100% sure. Be 100, let's say 110. I accidentally wrote that second one there, but it works out. Be 110% sure about solubility of polyatomics. Anions, to be specific. There's only one polyatomic cation that we will deal with, and that is going to be ammonium, and that is going to be soluble. Okay, and so if we want to determine whether or not the following compounds are going to be soluble or insoluble in water, we have to pay attention. So all chlorides are soluble, except when they are bound to mercury. So it's an exception to Rule 3 of solubility. Therefore, it is not soluble in water. And I'm just going to use that as the abbreviation. Potassium is a group 1 metal. This is an alkali. This is a halogen. This is exceptionally soluble. And so it will be soluble in water. Okay, so that's the rules. I would suggest what you should do is try and just pick 2 elements on the periodic table, that one's a metal and one's a non-metal, and see if you can find something that's going to be soluble. That's how I would suggest to do this. Okay, molecular equations. These are chemical equations where everything is treated as though it is a molecular substance, even though it may actually exist as ions in solution. And so what that means is that if you have an ionic substance or an ionic compound with AQ, that means it is soluble. If it was not soluble, then it would have S. If it would have an S, because that would mean it would be insoluble. For the molecular equation, we're just going to write everything as though it is all together, even though it is not necessarily. So CaOH2 is going to be soluble. We know that from the AQ. Na2CO3, soluble. NaOH, soluble, and CaCO3 is going to be insoluble. So that's calcium carbonate. That is, I believe, chalk. I don't remember off the top of my head. It indicates the states of the reaction of the product. So that's the molecular form. There's 3 different types of equations that we are going to go through, and this is going to be the second one. So we're going to take the molecular formula, we're going to note everything that's soluble, and then in the ionic equation, we're going to break apart those soluble things. So let's just go back real quick. We have CaOH2, CaOH2. When this breaks up, we get Ca2 plus 2 OH, no parentheses, OH minus. And so that's exactly what you see right here. You say a Ca2 plus and 2 OH minuses. We'll do the exact same thing with Na2CO3, and that's going to break up into 2 Na and 2 CO3. Now, on the other side of the equation, we have NaOH, and we have 2 of those. And so if we look down here, that's going to break up into 2 OHs, and it's going to break up into 2 NAs. However, for CaCO3, we do not write that broken up, not ionized. That's because CaCO3 is a weak electrolyte because it does not ionize that well. And so it's not going to ionize, and that's why we put an S. It's going to be a solid in solution. It's going to be insoluble. Okay. For the net ionic equation, the third of these equations, so we had the molecular, we had the ionic, and now we have the net ionic equation. All we're going to do is we're going to take that equation that we had before, and we're going to cross out all of the things that are going to be on both sides. So from CaOH2, that gave us Ca2 plus plus 2 OH minus. And then from NaOH, from this, we had, from 2 NaOH, that gave us 2 Na plus 2 OH minus. And so that's where we get this. 2 Na plus 2 OH minus, that's where we get those from. And so since in our reactants, we had OH minus, we had 2 OH minus, we can cancel that out. In the products, we also have 2 OH minus, so we can cancel that out. From our sodium carbonate, our Na2CO3, we also have 2 sodiums, which are also on both sides, so we cancel it out. And so the only things left are going to be what's in boxes. And so we can write the equation CaCO3 to make CaCO3. And so it's like a net gross income in the same kind of way. So it's the net is just taking out all of the differences, all of the things that don't matter. And so these here, these things that are floating that we're crossing out, these are called spectator ions. That's what those are. So, I want you guys to go ahead and just give this a shot right here. Try to balance this on your own, just this, and then use the answer that's present to be able to see if you got it right at the end. But I want you to give this a shot, and then I will talk about exactly why this reaction works the way it does. We're going to get into it in more depth in the next few slides, but yeah, this should have a specific meaning to you. Okay, so go ahead. Or what we'll do is we'll talk about this. So HClO4, this is going to be perchloric acid. You get out 2 H pluses. ClO4, we're going to cancel those out. We have 2 of those, we'll cancel them out. Ca2 plus. We'll cancel those out as well. We're just left with 2H plus and 2OH minus going to 2H2O. Now, if everything is divisible by 2, you must divide it. If everything is divisible, you must divide it. And it could be 3, it could be 4, it could be whatever. As long as they're all the same number, you divide it by that number, and so you just get a 1-to-1 relationship. And so you end up with this. Now, this is called perchloric acid. And this is calcium hydroxide. So this is a base, and this is an acid. Every time you have an acid and a base that react together, you will make a salt at the end. So CaCl O4, CaClO4 2, or well, that's not quite right. That's supposed to just be 1. But yeah, every time you get that, you end up having the same. This is going to be a salt, and then on the other product that you're going to get is going to be water. So for every single net ionic reaction between an acid and a base that does not include ammonia. Well, ammonia maybe as well, but every reaction that you're going to get between acid and base is going to be H plus OH minus goes to H2O. So all RXNs, that's short for reaction, with acid plus base have this as their net reaction. That being said, if the product that you make is a precipitate, so let's say that CaClO4 was a precipitate, then that would be then you would have a precipitate. So that would be part of your net reaction. A precipitate is formed. All reactions with an acid base are going to have H plus OH minus going to H2O as their net reaction, except if a precipitate is formed. Okay, and so let's talk about a precipitate. So a precipitate that is formed is going to be whatever if you have A, that is AQ, plus B, that is AQ, and you make, let's say that's plus and minus, and you make ABS, this is your precipitate. You can think of it like precipitation when we're talking about the weather. It's going to be a form of change in phase. So it goes from aqueous to being a solid, and so that's a change of phase. Just like with the weather. So precipitation, when we hear there's a 90% chance of precipitation, that's talking about how likely it is that it's going to rain. And so the precipitation is going from a gas in the air into a liquid that falls down. So that's a change of phase, a gas to a liquid. Acid-base reactions are going to be a transfer of a proton between reactants, and we'll get into this in the next slides, which I'm about to skip to in just a second. But a proton, specifically, we're talking about H+. So if we go to the periodic table real quick, let's just go there just for a moment and take a look at hydrogen. So hydrogen right here is it has one proton and a mass of 1, which means that it is most likely going to be just that one proton. Remember that protons and neutrons have about the same mass. So if there is a neutron present in that mass, it would be 2, but it's not. So it's just going to be 1. And so that means that it's H plus. And so if you have a hydrogen atom, let's draw it like this, with an electron present orbiting it, then you will you have a proton with a plus charge and an electron with a minus charge. And so that is going to be neutral. But if that electron is lost, and let's say we kick it out and go here, we have H with just one proton, and the electrons are going to be 0. And so your overall charge is +1, which is the same as just having a proton. So you get H plus. And so a proton is what is going to be transferred between reactants in an acid-base reaction. Okay, and so oxidation reduction reactions is something we're about to get into as well. These ones can get a bit more complicated, but they are reactions that involve the transfer of electrons between reactants. And so that's something like this. Let's say that we have Na sodium metal plus water, and we react them together. This is going to have 11 protons and 11 electrons. NaOH is what is made on the other side, plus H2, put a 2 here, put a 2 there, put a 2 there. And so the sodium now is going to be 11 protons still. We never change the number of protons when we're looking at a single atom, and only 10 electrons. And so you are going to get out of this Na plus. And so that is a transfer of an electron from one thing to another. So electrons go from having 11 to 10, which means that the transfer of electrons occurred. Okay. All right. And so let's go on to the next part over here and continue where we left off. So let's talk about precipitation reactions first. The precipitate is an insoluble solid. Insoluble solid. So that means that it is going to have a subscript S. So that is going to be some element or a compound with a subscript S that's formed during the chemical reaction. So that means that it is a product. If you have something formed during chemical reaction, it's the product. Precipitation reaction is written when written as a molecular reaction is going to be a double replacement reaction. And so we'll talk about exactly what that looks like right now, but let's show it real quick. We have A, B plus C, D. We're going to switch these around. So that's going to be CB plus AD. That is a double replacement reaction. It could also be a single replacement reaction. And so we could do it like this. A plus BC goes to B plus AC. So these two are switching. It's called a double replacement reaction when you are replacing two cations with each other. But A here is not a cation yet. And so this is just a single replacement reaction because there's only one cation. One cation. And this one has two cations. Okay. And so an exchange reaction is written as a molecular, when it's written as a molecular equation, it is going to exchange parts. But we are able to predict what kind of precipitation we're going to get. So the first thing we want to do is we want to take a look at the products. We want to predict the products. So we want to take a look at the reaction and predict what they're going to be. So for example, we'll have H, this is probably on the next slide. Oh, no, it's not. Okay, so HCl plus NaOH. And so this is going to be a double replacement reaction. We have two different cations. It's going to be like that. And so we can predict what the products are going to be because it's probably going to be a double replacement reaction. And so we end up with NaCl plus HOH, which is also known as H2O. And so this is a prediction of the reactant. And then we want to determine the state of each product. And so for this, I'm actually going to change Na to Ag. And I'm doing this for a specific reason. And so we want to determine the state of each product, the state of matter. And so HCl, we're assuming this is taking place in water. So I'll put an H2O up here so that we know what we're doing. This is going to be a AQ. I'm going to make this a little smaller as well so that it's a little bit easier for me to write. Small. AQ. This is also AQ, even though it probably is not in real life, but this is going to be a solid. I do know that silver chloride does make solids, and this is going to be a liquid. Okay, so that's the determining the state of each product. If all products, this is important. This one is very important. If all of the products are aqueous, then there is no net reaction. And so that's why I wanted to, that's not an excellent idea, but like, let's say that you have Ki plus NaCl. These two both are alkali metals. And these are going to be halides. So as long as halides aren't bound to silver, mercury, or lead, then they are going to be soluble, and all of the alkali metals are soluble, so we can say that this is going to be not S for soluble, AQ for aqueous. And then we will convert that to the double replacement reaction, but both of these are still going to be aqueous. So it's KCl plus NaI. And so we have AQ. Now, all of these are AQ. If all of the products are aqueous, then there is no net reaction. So we can say no reaction. Okay, let's continue. All right, so this is a big chart, and I'll probably give you guys one of these for the actual, well, not for this next exam, but probably for the next quiz that we do, and then also probably for the next quiz that we do, because it's going to be pretty useful. But the green letter, SOL, means soluble. The red letters, INSOL, that means insoluble, and the yellow ones are slightly soluble. And so slightly soluble means that it might become soluble, it might not. It depends. But the precipitation reactions are only going to occur if the combination of the two ions is going to be insoluble. And so one thing that I'd like you to notice before is that I said that all halides are going to be soluble except for when they have silver, lead, or where is it? Mercury. Where is mercury? Okay, mercury's not present, but silver, lead, or mercury. I'll put an Hg right there. And so that is true. We have chlorine all the way through, soluble, unless it has silver. That's not supposed to be like that. That's okay. But for iodine, we have the same thing. We have it's insoluble. This will also be insoluble. And this will also be insoluble. Okay, and so we're going to refer to this. So I'm going to clean it up a little bit. Going forward. Is this too small? Let's make it one more larger. Okay, cool. And so, all right. So the question is asking for us to determine if there is going to be a reaction between ammonium sulfate and sodium hydroxide. And so let's just go ahead and give it a shot, and then we will talk about it. So will there be a reaction. If there is no reaction, then nothing has formed. Okay, so yeah, give it a shot, and then we'll continue. Okay, so we have ammonium sulfate. That's something that's soluble. Then we also have sodium and hydroxide, something else that's soluble. I'm going to write it down here. NH4, we'll put this in parentheses. It's a +1 charge, so that's SO4. And then we'll put a 2 right there, plus NaOH goes to... All right, so if we do a double replacement reaction, we will get NH4OH plus Na2SO4. And so this double replacement reaction may make something. Let's see. NH4 and SO4, we already decided was aqueous. This is also aqueous. NH4 and OH is also aqueous. And Na2SO4 is going to be aqueous as well. We have that right there. It's soluble, so that's aqueous. Okay. And so one thing that I want to keep in mind is that when we were picking these, we picked this and this. The opposites are going to be what is made, right? So there's going to be kind of a square that's made. So let's say that you picked KCl and CaI2. Well, the products are going to be CaCl2 and Ki. All right, and keep in mind this is not balanced. That's okay, I don't mind. We're going to move on anyway. Okay, so if we were to do this with aluminum sulfate, which is a different compound, then we can check and see what is going to happen. So Al2SO3, this is going to be soluble. Sulfates are soluble for the most part, and so it's going to be soluble. Let's see, is that... Nope, the chart isn't here. We'd have to go back to the other one, and so I'm going to cue that up real quick so that we have it. The rules. All right, and so the rules say that sulfate is going to be soluble, and we have this as well. Sulfate will be soluble for everything except for calcium, strontium, except for alkaline earth metals. Alkaline earth, silver, mercury, and lead. Those are our constants. Okay, so, and then we can also go to this chart, wrong one. This chart back here, and we can see that we have aluminum right here and sulfate. That's going to be soluble. And then we have, the other thing that we have is sodium hydroxide, which we already know is going to be aqueous. So this is going to be soluble. Now we can go to aluminum hydroxide. And so we have aluminum, we'll go to hydroxide, that's going to be insoluble. So we know that we need to put a S right here. So that's insoluble. And so we're going to write the balanced molecular equation. And then we'll break everything apart that can be broken apart into ions and start crossing things out. So sulfate's going to be on both sides. Sodium is on both sides. The only things that are left are aluminum hydroxide and aluminum hydroxide. So this is our net ionic equation, is where we have aluminum hydroxide to make aluminum hydroxide. And keep in mind, again, there's 2 aluminums here, but only 1 there. There's 6 OHs here, but only 3 here. We just divided everything by 2 because we needed the lowest numbers possible. Okay, so let's move on to acids and bases. So this is just good knowledge to have. Acids are, they have a sour taste. So these are in energy drinks, tomatoes, and citrus fruits. Just as an example, those are going to be in energy drinks, tomatoes, and citrus fruits. That's where bases are. And we can use a, well, okay, so that's where the citrus, or sorry, these things are going to be acidic. And then we also have basic things. So basic things are going to have a bitter taste and be soapy to touch. So it's going to be something like milk of magnesia, if you've ever taken that, MgOH2. That's going to be something that is going to be basic. Let me think. Milk is sometimes basic, but that's not very bitter. It's not a very crazy thing. But soapy to touch is important. So probably you're going to feel a base rather than taste it. And so soapy to touch. And that's because NaOH, for example, is also known as lye. Lye is what has been used for generations to make soap. And it makes it from oils. And so the oil on your skin is going to react with basic ingredients, and you're going to get soap, like in your skin. And so to tell whether we have a solution that is acidic or basic, we use things called indicators, which is a type of dye that's used to distinguish it. And so it's going to change color depending on what kind of acidity or basicity it has. So this is where we get to exactly what an acid is. So an acid is going to produce hydrogen ions, also known as protons, in solution. Bases typically are going to produce hydroxide ions when they're in solution. So NaOH splits into that and that to make H plus, OH minus. That's how we get our basic solution. And so one of the types of acids, there's a few different types, is going to be a Bronsted-Lowry acid. And so again, if it donates a proton, it is a Bronsted-Lowry acid. If it accepts a proton, so that's different than donating an OH, but it's basically a very similar mechanism, then it's going to be a Bronsted-Lowry base. And so let's take a look. Does it explain? Yes, it does. So Bronsted-Lowry acids and bases. So all of the acids we've discussed so far are going to be Bronsted-Lowry acids. These are going to be the common ones where you have binary acids, HCl, hydrochloric acid. We have nitric acid, sulfuric acid, phosphoric acid. And then and so the way to identify these is going to be if the H comes first. So the one exception to that is CH3COOH. This is acetic acid. And the H comes last for this, but it is separate from the other H's because it is an acidic proton. And what that means is that when it goes into solution, I'll just draw the products over here, you get CH3COO minus plus H plus. And then for bases, for Bronsted-Lowry bases, we're talking about NaOH. Anything that ends in OH is going to be a Bronsted-Lowry base. That's because if we have something like NaOH plus HCl, for example, we have something donating a proton, this HCl, and something accepting it. So you end up getting OH minus getting added to an H plus, and then you end up getting H2O out. So this is going to be accepting this proton, and so that is going to be the definition. The other one is going to be this, NH3 plus H plus is going to end up with, you start with ammonia, and we end up with H4 plus ammonium. There we go. And so that's another way. So ammonia does not have an OH on it, but it still accepts an OH. It still accepts an H plus. So we can say that it is a base. A strong acid is going to be something that ionizes completely in water. So just like NaCl completely ionizes to make Na plus Cl minus, HCl completely ionizes in water to make H plus Cl minus. So a strong acid completely dissociates in water, completely ionizes. Hydrochloric acid, HNO3. Most of the acids that we have covered so far are going to be strong acids, but there are some weak acids. Weak acids only partially ionize in water. So that means we have HCN, and it's going to do this arrow again. It's going to go back and forth between H plus Cn minus. So something that's not written here is that when you have a reaction with HCN on both sides, let's say that we have HCN. Well, we'll see it in the next one. Actually, I'm not going to cover it quite yet. And so if we want to dive a little bit deeper into what acids do, this is what happens. So when you react a strong acid with water, that proton is going to go to the water and make this. This is called hydronium. And it looks like this. You have an O with an H and an H, and then there's another H. It's like water, it just has another H coming off of it, and it has a plus charge. And so you have that attracting, and then you also have the counterbalancing ion. And so this is what we measure pH with, is the amount of H3O plus that is present. So that is the amount of acid that's present. And we'll get to pH at some point. And so this is what this is going to look like if we were to look at the actual atoms. So when we have HCl going into water, you get H3O plus Cl minus. And so you can see the H3O pluses in solution here. These are our H3O pluses surrounding there. We also have Cl minus, where those are going to be, those are separate. But with HF, it's a little bit different. So HF is I'll label this as a strong acid. That means that it completely dissociates. So it completely dissociates. HF is a weak acid. It partially dissociates. And so if you were to look, you would see that you have HF, 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 and then every now and then you will get an H3O plus and an F minus, but it's not going to be as common nearly as if you were to do it with a strong acid. And so that reaction would look like this. HF plus H2O goes back and forth between H3O plus F minus. And so it might spend 90% of the time over here as that and 10% over here. Whereas this would spend just about 0% of the time and 100% of the time. That would be the difference. Could be something other than 90. We'll get into exactly how to calculate it at some point. Strong bases. Okay, so strong bases are exactly they're very similar to strong acids in which they are strong electrolytes that completely dissociate. So if you have NaOH going to Na plus OH minus, then you have 0% NaOH and 100% Na plus and OH minus. Weak bases like ammonia, like I said before, NH3 plus H plus is going to go back and forth between each of these. So it's going to be NH4 plus, and let's say that it's like 10% or something like that, and then there's 90%. It is not a complete dissociation. It is a weak electrolyte. It's a weak base. But it's called a base because it interacts with H+, whereas it's not necessarily considered an electrolyte. It is considered an electrolyte, but not in the same way. Okay, and so go ahead and take a shot at these. Let's see. Try not to read the bottom part, and let's see if you can come up with whether or not these are going to be strong or weak acids or bases. Okay, so lithium hydroxide. When we break this apart into water, we get lithium plus OH minus. And now lithium is an alkali. Metal, which means that everything dissociates with it. So this is a strong, I'm just going to put an SB. And we know that it's a base because it has this OH here. Now this is acetic acid, HC2H3O2. It can also be written like this. It can also be written like CH3COOH. Now this is called an organic acid. Organic acids are generally weak. And so organic acids are generally weak, which means that, and specifically organic acids, remember, in order for it to be organic, it has to have carbon and hydrogen bound to each other in the model, in the compound. And so we have a generally weak acid here. HBr. Br is going to be, these are classic strong acids. Bromine, everything dissociates with, as long as it isn't lead, mercury, or silver. And so we get out H plus Br minus, and this is going to be strong. SA. And so since it donates an H plus, it's an acid. Since this one would also donate an H plus to get CH3COO minus plus H plus, this would be a weak acid. HNO2, it looks like it's about to be a strong acid, but HNO3 is a strong acid. This is nitric acid. This is nitrous acid. Nitrous acid is not strong enough to be a strong acid. It will dissociate into H plus NO2 minus, but it is only going to do it partially. So we'll draw that back. And just for clarity, I will also do the same to this. We're going to draw an arrow this way and an arrow that way because it is going to not completely dissociate. It is a weak acid. So this goes for anything. All of the 8s will be, or the 8s and ic acids are going to be strong. all OUS / ites will be weak. Nitrous acid is weak. Nitric acid is strong. Phosphorus acid is weak. Phosphoric acid, I believe, is strong. I don't remember, actually, off the top of my head. Okay, so for a neutralization reaction, something that we've covered before, this is when you have an acid and a base that is going to result in an ionic compound, a salt. It says it down there, but I'll say it again, and probably water. And so we have a strong acid, we have a strong base. When they come together, you end up getting a salt and water. This is one of those situations where you are reacting an acid and a base together. The net ionic reaction is going to be H plus OH minus goes to H2O. And we know that because everything else is going to be aqueous. The only things that are going to matter are the things that are going to contribute to making H2O. So let's write this out. And so keep in mind that this is going to be a weak acid. And so one thing that I want to note about weak acids is that when we write them out, they do not completely dissociate when we write the ionic equation. So HNO3 stays as a complete thing. Okay, I'll give you a chance to do this, and then we'll go through exactly how to do the molecular ionic and net ionic equations. Okay, so we have HNO2AQ plus NaOH. Make that go to do the double replacement reaction. So that's NaNO2. And we'll put an AQ here, an AQ here. I oftentimes forget to put the states of matter, but I will do my best to remember. And we have H2O on the other side. And so HNO2 is a weak acid. And so I will say WA for that. And so it's not going to dissociate fully. And so when we write our ionic equation, we'll keep it the same, HNO2AQ plus Na plus OH minus. And we'll put AQs here as well. Make that go to the product. So NaNO2 does indeed fully dissociate because we have sodium. Sodium is an alkali metal, so it's going to fully dissociate. We have Na plus NO2 minus, and that's going to go, we're going to add H2O. And remember that this is going to be it's a type of precipitation. It's really a neutralization to make water, and especially if it's in water, you won't be able to tell the water that you made from the water that was there already, so we don't really call it a precipitation reaction, but we do have something changing phase. And so now this is our molecular, this is our ionic. And to make the net ionic, we just have to cancel out things that are on both sides. And that's it. That's all that's on both sides. It's just Na. So we end up with HNO2AQ plus OH minus goes to NO2 minus plus H2O. And we'll put in the AQ, put in the AQ and the liquid. And let's go and see that is true. So the only things that crossed out were Na+. The only things that are left are going to be the things that were not crossed out. And there we go. That's our net ionic equation for a for reactant, and we're using, and so this is the most important part, is that if you've practiced this enough, you do know how to do the molecular ionic and net ionic equations. But what is important is that if it does not fully dissociate, then it will remain as molecular in the next equation. Okay, so let's talk about different types of acids. We have polyprotic ones. Poly meaning many, like a polygon has many sides. A polycule has many people. Protic means it has a proton, but polyprotic means that it has at least two or more acidic protons. So for example, we have H2SO4, H2SO4 and H2O. And go ahead and give this a shot right here, H2SO4. You're going to need to balance this equation, but go ahead and see what it would make. Keep in mind that we have H2O, and so adding a proton, you can only add one proton to H2O. And so that's how you will need to balance it. And so what we get on the other side is H3O plus SO4 2 minus. And so we need to balance that out. Put a 2 here, put a 2 here. There we go. Sometimes the precipitation is going to be a gas. And so you might get something like this. So specifically, if you have a sulfide that you're reacting, a carbonate or a sulfite, those are going to be reacting to make a gas. The most common one is a carbonate, though. So carbonates do this, where you make, well, let's do the first part of this reaction. So the first part of this reaction is carbonate and the acid. We're going to take this H and replace it with here, and we get H2CO3 plus NaCl, right? And so that's not what we show down here. And the reason for that is H2CO3 is a specific type of acid that you're making. It's called carbonic acid. And what it does is it will become H2O and CO2. It will decompose into becoming H2O and CO2. So H2CO3 goes to H2O as a liquid and CO2 as a gas. And so that's why we see H2O and CO2 here, and we don't see any of the CO3 2 minus ion there. And this is exactly what we see down here. Once we do this change, that's what we see. But the reaction goes further, one step further, and makes water and carbon dioxide out of this reaction. And so that's what this is. Vinegar is acetic acid, CH3COOH, and baking soda is NaHCO3. And when you react them together, you get a whole bunch of bubbles. Gas evolution. It's called gas evolution. And you get out CO2 from the reaction. Okay, give this a shot, and then I will be back to help. Okay, so zinc. Zinc is one of our magic three. So with AgZnAl, we have Zn as the second one. And so Zn is going to have a 2 plus charge. So, and sulfide is right below oxygen. So it's most likely going to have a 2 minus charge when it's bound to a metal. And so we have Zn with a 2 plus and S with a 2 minus, and that gives us ZnS. And now hydrochloric acid, remember hydro means that we just have that hydrogen, and chloric would mean that it is going to be a chloric means that it is going to be a binary salt. Hydrochloric, if the hydro is there, it means it's going to be a binary salt. So we have HCl. So ZnS plus HCl goes to ZnCl2, because each one of the chlorines has a -1 charge to balance out the zinc's positive charge, plus H2S. And so we'll just put a 2 right there. That way everything should be balanced. We put in the states of matter. We have AQ, let's say.